Hello. Hi guys, welcome back to the new video. Ki hal chal, sab changa si. I hope that you guys are doing good. So in this video, we're going to see the problem. Find unique binary strings. We'll see all the variations, as in from the very basic brute force to actually optimal, more optimal, more optimal, more optimal. Like we'll see 4 optimalities for it. Cool. Let's see. Let's start. Begin with the question. So, well, the problem says we are having an array and of strings nums containing any unique binary string. Again, it contains n unique binary strings, each of length n. Okay, we have n strings and each of length n. That's also a plus point, which is for us to remember. Each of length n and n binary strings which we have. Cool. We have to return a binary string of length n which does not appear in the nums. So which is not in the nums itself. We have to return that particular string for us. If there are multiple answers, because for sure it can have multiple answers, we can return any of them. For example, if you just take this case, so you will see that 101 as a binary string is not appearing in this 111, 00010 and 001. So for sure that can be an answer. Again, answer can be also 000 because it's also not appearing. Answer can be anything which is not in my nums. So the first very brute force thing which comes in my mind is, okay, it's just a binary string, right? I have to check if it is, okay, I have these input as n strings and I have to make a binary string of length n and then check if it is there in the input or not. So rather what I can do is I can make my all binary strings which is having that 10, which means I know the length is n. So how many such binary strings I can make? I can make 2 raised power n binary strings out of it. Now what I will do, I'll just consume that and I'll say, okay, this is my input right now. This is my new input. Now I'll just hash these strings, these n strings out. Right now, when I have to say n of nums, so I'll just say, as in the number of strings are n, the length of strings is also n. So I'll just say number of strings and length of strings. So I want to hash all these n, the number of strings. So I'll just hash all these strings out and say, okay, 111 is present, 011 is present, 001 is present. Now when I am making all these 2 raised power n strings, because ultimately it can be how to raised power n, at every place there are 2 options, 0 or 1. Place a 0 or a 1, place a 0 or a 1, place a 0 or a 1. So 2 options for it, 2 options for it, and again two options for every of the characters. How many number of characters? N characters I can have, because the string, this string itself is of length n. So for sure the options are to reach for n. So what I can do is simply make all the strings out and check, okay, I can just, next when I have made all these strings out, I can just simply iterate on all of these strings, which is 2 raised power n strings, and while I am iterating I can check, okay, is that in my hash set or not? Is that in my hash set or not? Is that my hash set or not? So with that I can simply achieve my result. But you will see that n is, like for sure it can work, because n is just 16. It's pretty small. So for sure this approach can also work, in which you find out all the strings possible of that particular length n and then just check, okay, was that in my hash set, was that in my hash set, was that in my hash set or not. So you will see that it will be nothing but a 2 raised power n. Now just to check a hash set, it just takes O of 1 operation, so that will be nothing much. So with this, and it's a simple recursion which you can apply, as in what you will do is, you know that, okay, it's your now one way is just simply make all the strings first and then ultimately check after making all the strings, or other ways, while making the strings itself, meanwhile check, which means in your hash set, firstly hash things out, okay, not that hash but simple hash. So firstly hash things out, which means 100, 010, 110, like these are 3. So I'll just simply hash it out and say, okay, it is there, it is there, it is there in my hash set. Now when I'm doing my recursion and I'm just iterating and building all my those strings, 2 raised power n strings. So while I'm just checking, which means you can have a base case, we'll go into base case later, but ultimately at every current string I just try to push in a 0, and at every current string I'll try to push in a 1. At any point of time, if I can get any of these strings, and ultimately in my base case I'm just checking, okay, as soon as the length reaches n, I can just check if that was in my hash set or not. If that was not in my hash set, then simply return that, because I have found a string which is not my hash set. Else simply return an empty string, just to have a check that if the empty string is being returned, it's not a valid string. So please don't don't consume that, only consume the string which is non-empty. So just a condition that to know that the string which is being returned is valid or not. So with this, you will see that in worst case, it can actually go to 2 to the power n chances. Now that is simple point which we put out, that okay, we'll just try on, like first thing we saw that we can just try on all the possibilities, which is 2 to the power n, and then we can just check hash set. But then we thought of, okay, meanwhile, while making the like strings itself, which is these strings, meanwhile we can check if that was present, if that string is not present in our hash set or not. So we saw that okay, it can have a complexity of 2 to the power n, but I'm asking you, is it actually the case? Is it actually the case that the complexity is exponential 2 to the power n? No. So if you have ever heard of pigeonhole principle, so it's not exactly pigeonhole principle. Like pigeonhole principle just says that if I have 5 pigeons and 4 objects, for sure in one box 2 pigeons will come for sure. That's a pigeonhole principle. But similar to that is this, like it's just a similar kind of principle. You can just classify this as a pigeonhole principle type, that if I have, let's say, 3 pigeons named as A, B and C. Now if I have, let's say, 5 other pigeons, in this case I had n pigeons and 2 to the power n pigeons. Like when I say 5 other pigeons, I'm just saying, okay, I have 5 other pigeons, which is, let's say, question mark, question mark, question mark, question mark. Now out of these 5 pigeons, I have to figure out one pigeon which is not in these 3 pigeons, right? So A, B, C, I have to figure out any of these, which means I have to figure out in this particular input of 5 pigeons, just one pigeon which is not in my above 3 pigeons. So what I can do, like, is it actually required to go on to all the 5 pigeons to just get one pigeon out which is not in the above? I'll say no. Just go, if you know that you have X number of pigeons, which is A, B and C, so just try for X plus 1 pigeons out of those 5 pigeons, so that you can just get one pigeon out. And why Aryan this X plus 1 will work? Because in worst case it can happen is that all the X pigeons, which is these all starting 3 pigeons, are exactly A, B, C, A, B and C. Then when I will check for the 4th pigeon, for sure I'll get a pigeon which is not in A, B or C. So it is just that you have an input of 3 pigeons, so just try for 4 pigeons at max. You don't have to try for all the 5 pigeons, or let's say it would have a 500 pigeons, so you don't have to try for all the 500 pigeons. For sure at max, in the worst to worst case, if you just go and sequentially try for the starting 5 pigeons, you will, or basically any 5 pigeons, you will try, sorry, any 4 pigeons, which is X plus 1, X plus 1. If you try for any of the X plus 1 different number of pigeons, for sure in that itself you will find a pigeon which is not inside your these X pigeons, because it's plus 1, right? You're just trying for one more pigeons. In worst case, you can match X pigeons, but not X plus 1, because you only have input of X pigeons. That's the reason what we can do is, in this above example was that we know that we only have n strings as an input, but we are actually building a 2 to the power n strings. So while we are building it, and we also know while we were building it, we are also checking it out. So in the worst case, this can actually go to just n plus 1, and that is it. After that, it will not go, because in this n plus 1 chances itself, it can find the string which it wanted, and then it can simply return that string. So this function which we wrote, so it's a recursive function, so for sure it will go and try for building one string at a time. So it will just go and try depth first search, build one string and check if it's there in hash set, then come back and then try to make other string, come back, try to make other string. It is how a DFS or a recursion works. So it will go in depth and try to make that string. Okay, one chance done, other chance done, other chance done. So as soon as the n plus 1 chances are done, for sure it will be returning something which is valuable for us, which is the actual answer, which is not in those n strings. And that's how this thing which we saw earlier, which we were thinking that would go to 2h power n times, will actually go to n plus 1 times itself. Now just one thing, although in C++ world you can do a string dot pushback of a character, which is that a mutable string, which can actually make this operation a O of 1 operation. But if you don't have a mutable string, as in other languages. So this operation will also cost the O of n operation, because you have a string of length n. If you just add a character, so again that will be of length n. So basically you are just having an operation on a string length n. So that's the reason this can, which means this addition operation of a character inside a string, can act as an extra O of n character. So this will have a complexity of O of n for sure. Just simple recursion will go just n times, but this string like modification operation can also be O of n. So please make sure that it can have a complexity of O of n square. Space will also be O of n square. Why? Because for sure you will, in a hash set, you are hashing out all these strings, n strings, hashing out all these strings. Every string is of length n. So for sure hashing itself will take a size of O of n square, and for sure the recursion itself, recursion is nothing but a DFS, so it will also have the internal stack space which it will take. Let's see the code quickly. Again, it's not the most optimal code, it's still space and time of what is we are thinking. Okay, it's not much because our n is pretty small, it's 16, but still we'll actually will optimize it more further. But let's quickly see the code. It's simply as what we saw above. We have a base case in which we'll have a num set. This num set will just say that all the strings in nums, just hash them out and insert in your num set, and then go and quickly call the solve function. The solve function will go and firstly it will try to add a 0. It will try to add a 1. When it will try to add a 0, it will just check whatsoever is returned. If it is actually not empty, which means this is not empty, which means it has not been in the num set, then for sure return that answer. Else you can just simply go and solve for current plus 1, and for sure this will return the answer, because we are actually bound to return the answer because the question says that you will return the answer. So with this fact you can easily solve it. But is it optimal? No. Can we try it better? Yeah, we can. So what we saw above, we can just use the same thing. Earlier we were using strings, and we know that we can convert the binary strings to numbers. So rather using strings, because you saw now that because of this thing of modification of a string, you were actually consuming much more time and space. So rather being going in the string format, can't we go in the number format? Because we can convert binary strings to numbers very easily. So what we will do is, we know that we'll use the exact same kind of same binary, the pigeonhole principle, but we'll just convert those strings to numbers. What will happen now is, we have these 3 strings as an input. It's just example 3 of our question. We'll just convert those to numbers itself. We'll convert this to numbers. It will become like this. And just simply, if you don't know how to convert a string to numbers, in C++ is just a string to integer. If you just pass a integer, which means if you just pass a string, let's say if I pass a 101, so if I just do a string to integer of this 101, it will just make a 101 as a number. But I know that this number is in base 2, so I'll pass a starting index. Okay, starting from this index, you have to do in a base 2 as a number. So I'll just pass string to integer that particular nums of I, and then starting positions, and then the base. Okay, it's a base to number. So with this I can simply convert my string to an integer. Now when this is done, again the same concept, try for the starting x plus 1. I know these are x number of, or basically n number of strings, so I'll just try for n plus 1, starting n plus 1. I have 3 strings as input. I'll try for the 4 strings, or 4 numbers, starting 4 numbers. I'll try for 1, 2, 3 and 4, or I should say 0, 1, 2 and 3. If anything, again I said, try for any of the n plus 1 numbers, still you will get the answer. So I'll just try for the 4 numbers, any 4 numbers, and for sure I'm bound to get answer in that. Now, but try that number, I have hashed as a number, so I can try. Okay, let's say I know that 1 is not, okay, 1 is there, so that could not be answer. 2, okay, 2 is not there, so 2 is the answer, but I have to return the answer as a binary string, not as a number. So now when I have got the answer, I know that 2 is the answer, but now convert this 2 to a binary string. So what I will do is, I will simply convert this 2 to a binary string, but of size n itself. So as you know that the string maximum length is actually 16. So what I can do is, one way is just manually converted by using a function. Other ways you can use a bit set. So bit set is nothing but you can represent a number as a bits. So what I'll do is, I'll convert this number 2 as a bit set of length 16. Okay, this bit set 16, this number, we actually convert this number to a bit set of length 16, and then I'll convert this bit set to actually a string. Now this bit set which is actually 00010 has become a string, but now you know that I have to only take the last n characters. So what I will do is, whatsoever string I have got, let's say s in this case, I'll just convert and I just take the last n characters of this string by using a s dot substring of 16 minus n, because I know the length is 16 because I have made a bit set of length 16. So I just convert this 16 length bit set, or basically string, now ultimately to a last n characters. I'll take and convert that to a string, and I'll ultimately get this particular string right here. So it's just a simple string to integer. Just hash the integers out and just check for the n plus 1 integers, and then ultimately convert that integer which you have got as the answer back to a string by making it a length 16, converting that to a string, and then converting that 16 length string back to a 3 length string, which is last figure, like last three characters, and then giving that as an answer. So again, that will be of, we'll see why the time is this, but that will be time of O of n square and space of O of n. Now how this is done, exactly same as what we saw. Firstly, we will just have an unordered set. Again, we will just have iterate on all the strings. Every string I'll convert that to an integer of base 2 and then insert that in my set. Now when this is done, I will again go to all the n plus 1 numbers. See, I'm going on to 0 to n. I'm going on to n plus 1 numbers. I'll go to n plus 1 numbers and say, okay, if that is inside, that is not inside my set, so that's my answer. If that is my answer, bro, convert that to a bit set, convert that to a string, and then take the last n characters of that string and return that as an answer. So with that I can just simply get it solved. Now converting, which means iterating on all the n strings, okay, iterating on all the n strings, O of n operations. Converting a string to an integer of length n is again O of n operation, because string is of length n itself, so that will be O of n square. And this iterating on all the n plus 1 like numbers, it's O of n plus 1 plus O of n to convert that number to a string, so that will be O of n itself, you can say. So that's the reason that the time complexity will be actually O of n square, and space is O of n because I'm consuming a hash set of n integers. It's just n integers itself, so that will be just O of n itself. Now again, we have optimized quite a lot in space, but can we optimize it much more further? Yeah, we can. Let's see how. So now what we're going to use is a simple trick. You don't need to know Cantor's diagonal argument or anything like that. It's just a algo or like kind of a concept, but we don't need to know anything about that. Don't even remember the name. But the only concept is, what you wanted was something which is not inside those n inputs. So now you know that you have these n inputs. So how about I just try to make a string out which is considering, okay, I will not consider the first string, second string, third string, which means I want an input of size 3. I want an input of size 3. I want an input of size 3, right? So what I will do is I'll just say, okay, bro, I want a string which should not be same as this, right? So if I just modify one character of this string, just one character, the first string, if I modify one character, for sure it will not be same. So what I will do is, I know that I can modify one character, so I will just modify one character, and I can modify any character. For simplicity, modifying the first character of the first string, I modify this character and make it opposite. Now I don't know whatsoever the remaining part is, but as I modified the first character, for sure it will not be same. For sure it will not be same as with that of the first string. That's good. For the second string, I should not modify the first character itself, because for sure I have already modified it, and if I just modify it back to other number, it might actually become same as the first string. So what I'll do is, for the second string, to not make the string output string same as the second string, I'll modify this second character. Okay, I'll just modify that characters. Oh, for sure. Now this string which is being built, okay, it's a 0 0 which is being built right now, it is for sure not same as these two strings. Now again, for the third character, I'll again say just modify the third character for it. Okay, I'll just modify the third character and I'll get again a 0. So with this, you will see that what I'm trying to build is, I'm trying to say, okay, for the first string, just take a character which is the first character, and I'll just make opposite. For sure, the output which I am forming right now, I'm making it bound to not match of that of input. and I'm doing it for every character. Thus, the string which I have formed ultimately will satisfy that it never matches third, second, or first string. And that's the reason this can be our answer. Ultimately, what we did was just going on to these indexes, flipping them out and returning a opposite value and adding in your string. That's it. You are doing nothing else. And that's the reason this can be solved. Now, Aryan, what if I had other string also of length n? For sure, you could not have done this. Why? Let's say I had other string 110. So you need one more space. You cannot modify these existing 3 space. So it was possible only because it was n strings of length n. That's the reason. Cool. Let's quickly see. It's pretty simple. We'll go on to all of our n strings. Right, for every string I'll go on to that specific II character, as I showed you. II, right, II characters. I went on and I just said, okay, if it's a 0, take a 1. If it's a 1, take a 0. So just take opposite. So I'll just take this, I keep on adding in my answer, and I'll simply return that as an answer. You will see I'm just going on to all the n strings. So that's the reason, the complexity of n, and nothing extra space is being used. So it's over fun. Again, it's just one thing, that this operation of answer plus of that particular character, it's a costly operation. So rather use an answer dot pushback of that particular character, because that will actually increase your time complexity. So make sure that you actually modify and use answer to pushback rather than just adding your character in your answer, or basically a string in your answer, because adding a string or character in your answer actually increases time complexity. Cool. I hope that you guys got all the 4 methods from exponential to why exponential was not an exponential, to converting that to a number so as to reduce the space, and then ultimately to a most optimal solution, that just considering that all the strings, I am just trying to make a new string output string different from all the strings. Cool. Thank you for watching. Bye bye.